It wasn't roasted. I was saying that you were probably thinking, oh, I'm just going to not do this. Anyhow. Okay, science time. Let's talk today about waves. ¿Cómo se dice waves in español? Does anyone know? Do you guys know anything about Spanish at all? I thought you were all in Spanish classes. ¿Cómo se dice waves? I like this because, ¿cómo se dice hello? Nope. I want you, I don't normally go out of my way to make fun of what someone has said. You know me, I'm very nice, I don't make fun of people. But when I asked ¿cómo se dice hello, someone said aloha, which I think is funny. It's really, it's yeah. So ¿cómo se dice hello? No. Hola. And you say the word for wave is spelled different, but it is also hola. Hola is O-L-A. But you know, like when you wave, you say hello. Whatever. Anyway, that's how you can remember the word Spanish is. The word wave in Spanish is hola. Okay. What is a wave? Well, let's define wave. You should already know all of this. As I've said, this is the 4th time in this class I've said this. What is a wave? How could we define a wave?
Thing that goes like that.
Let's not use that definition. Okay. And is it a thing? Is a wave a thing? It can be made of things, but it's not itself a thing. You can't take a wave and pack it up in a box or a moving van and give it to your grandma. What can you do? What is it then?
Control it.
Okay, what is it? You can change its stats. Yeah, you can change its frequency and direction and all that. So it's an entity of some kind, but it's not a thing. It's not a physical thing that we can touch. It might be made out of physical things, even though that's not always true. It does transfer energy, but what should be the noun sentence? We can't just put waves transfer energy, because that's the thing we're trying to define. What transfers energy? What is it that transfers energy? Waves are well, what other kind of things do we have or I shouldn't say things. What other stuff do we have in science besides things themselves? We also talk about the what's that apply to these things. Yeah, so matter and the what's the idea, what other thing? Well, I'm going to leave that blank. So it's something that transfers energy. And that is important, that we know that they transfer energy. And we're going to put in a specific way, too. And these two things we're going to say are going to kind of help us define wave. What must a wave do in order to be a wave? It doesn't have to travel through a medium. Some waves don't. Light waves do not have to travel through a medium. That's a good guess, though. Okay, so yes, it can be, it may have a trough and a crest. Not all kinds of waves have that either, though. They do transfer energy. That is true. Light can, so some waves, like light waves, electromagnetic waves, can transfer energy through a vacuum, but not all waves can. So we shouldn't include that in our definition. Well, let's diagram wave and see if we can get another guess. So there's two kinds of waves, as you know. What's the title of this wave? This is a really good wave, if I do say so myself. But what's the title of this guy? Which type of wave is this? Transverse wave. Thank you. Transverse wave. And then here's another kind of wave.
Compressional.
This is going to be a compressional wave, as some people have already discovered. Or sometimes we also call it, I forget which one your book calls it, but we also sometimes call it a longitudinal wave. What is true about both of these? Yeah, okay, that's exactly what I'm getting at. That's the second word here. A what specific pattern? It has to be a pattern that, and kind of the word in pattern does imply this, but it has to be a repeating pattern. So it's something that transfers energy in a repeating way. It has to be repeating, or it's not a wave. I'm going to put the word that in here. Now we're still at the thing. What is it that transfers energy in a repeating wave or way? We still have to have a noun in this sentence. Can't use wave, right? We already said that, but that would work, wouldn't it? A wave is a wave. Yeah, what? Disturbance. I like that. Disturbance is fine. Disturbance that transfers energy in a repeating way. The one I was initially looking for was a process. Everything that we're defining in science is usually either a thing or a process that applies to things. Remember, like we had, trying to think of anything, like an atom is a thing, and then a force is a process that applies to things. So a disturbance that transfers energy in a repeating way, or a process that transfers energy in a repeating way. And we already have our two kinds of waves here, transverse and compressional. Let's label them up real quick. You should already know this. We should have a little counter over here for how many times this boy has said you should already know this, because do you think you should already know this? Yeah. What this? What this? No, it isn't. You can't just go by you can't just memorize the order they go in on your vocab and say them.
Is it the rest position?
No. I'm pointing at this little tightly packed group of doodlies. I'm gonna put this one down here, sorry. I see how that was confusing.
Is that like from the top of that? Or like, is that
This is for a different kind of wave. This is for the compressional wave. These are two different kinds of waves here. What's this part of the compressional wave called? No? Okay, you should know this. You said the wrong one, I think, but I'm going to put the right one and give you the benefit of the doubt. You know, that's one of the nice things you could learn from this, some of you boys, of saying things really quietly. Someone might think you said the right thing, even if you said the wrong thing. This is a compression. They're compressed in this area. What are they? These dots represent particles, matter particles. Compressional waves can only travel through matter, and so these little dotties represent matter particles. What's a nice science word that someone already said today for a matter particle? An atom would be fine, but they're not all atoms. There could be an atom or a molecule or a formula unit or an ion, but some matter particle, some particle of matter, when it's compressed, shut up. When it's compressed, it's called a compression. What about when it is spread out? That is where it's called a rarefaction. And that's analogous to this part of the transverse wave, which is called now you get to say your word. Good. In both cases, and I endeavored to draw these both kind of in line with each other, so I only had to write this once, but in both cases, this one point on a wave, either the crest or a compression, or it could be a rarefaction, or it could be right where the compression goes into the rarefaction, doesn't really matter, but the one point on a wave to the next point on a wave, this distance is called, some people are just guessing vocab words, but some other people are saying the right one, which is wavelength, and that has the symbol lambda, the Greek capital letter lambda. I think that's actually the lowercase lambda. Either way, I'm pretty sure it's late. But this is the Greek lowercase letter lambda. You should write that down because that stands for wavelength. And some people keep guessing all of these wrong and just guessing random vocab words, and some of those same people are not writing these down as I'm writing them down, so you should probably do that. So a wavelength is one point on a wave to the same point on the next wave, and we abbreviate that. The symbol for that is the Greek letter lambda. What kind of units do we use to measure wavelength? No? Say it again.
millimeters?
Yeah, does it have to be millimeters? No, any what unit? No, not any metric unit, because Celsius won't work.
Oh, no.
Any what unit? It doesn't even have to be metric. Yeah, but yeah, a length measurement. It has to be a length measurement. So measured in units of length. Units of length. I would imagine that there would be, I don't think NASA would do this to me. I don't think they'd betray me like this. Maybe in the 60s, NASA even measured wavelength of waves like this in feet. I can imagine that would happen. If it is a length unit, it would work. It'd be messy because anytime you try to divide it, it would be a huge circus. But yeah, it would work. You just have to have some kind of length units. If you were very careful about your conversions, you could measure it in Payton hand width if you wanted to, or I could just measure in hands like you measure the height of a horse. You could do that. You could measure the wavelength of a wave in hands. Why would you want to? I can't even imagine. But it is a length unit. It would work. Okay, well, speaking of some other people shouting vocab words all the time, what do we call this? With the distance from crest to trough on this stuff, and we'll talk about in a second how we measure this on a compressional wave, but what is this called on a transverse wave? Amplitude. Not who I was expecting, but that's fine. Amplitude. And now listen, this is very important because you can get this wrong, and I don't want you to. On a compressional wave, amplitude is, Colton, be very careful to listen, because you may not understand this, and I want you to, because otherwise you'll do bad. On a compressional wave, let me try again so that you can pay attention even this time. On a compressional wave, amplitude is how tight the compressions are and how spread out the rarefactions are. That would be a high amplitude. So if these kind of blend smoothly together, that would be a low amplitude. Like if you can barely tell the difference between a compression and a rarefaction, that's a low amplitude on a compressional wave. And if there's a distinct compression and almost nothing, in fact the highest amplitude compressional waves would have all the matter squished into compression, tight bands of compressions, and vacuum in between. That would be the highest amplitude compressional wave. So in this, amplitude equals how compressed the compressions are. Does that make sense? Uh-oh. Well, I'm going to explain that back to me in a second. How compressed the compressions are and how spread out. We could say rarefied. The rarefactions are spread out. The rarefactions are. Looking at the diagram on page 292 of this calls it a coiled spring toy. Those of you who aren't afraid of copyright strikes are going to call it a slinky. But if we look at the picture of this coiled spring toy, can you imagine, based on what I just said, what would this diagram look like if it were it is a compressional wave. What would the diagram look like if the amplitude were lower than it is here? What would that look like? Yeah, that compression, you mean. That compression would not be as tightly packed as it is now, and the spaces between the compression, or the spaces on either side of the compression, would be a little bit closer together. Basically, the compression would be less compressed, and the rarefaction would be closer together. If it were higher amplitude, what would it look like? Well, it might be that all but one of those little coils was smooshed up into the compression, and all that was left on either side was just one really stretched out coil as the rarefaction. Okay, let's move on to some other steps. What do we call the amount of waves that pass by in any given second? Or not even just a second, but any given unit of time? No? Wait, the way I phrased it, no. Frequency. The frequency, which is represented by the Greek letter nu. Oops, I should magnify this. Oops, I should magnify this. Oops, I should magnify this. Okay, there it goes, finally. We use the Greek letter nu, which in my mind, Colton, please pay attention. In my mind, not just in my mind, but in my handwriting, I differentiate this from my letter U or my letter V. In fact, I usually make it pointed, but the marker is kind of fat. Anyway, I just put a little tail here because it does look pretty the same. But this is the Greek letter nu. I should indicate this is lambda. And that's what we use for frequency. Although I think your book uses the Latin letter F, just kind of curly Q like that, which is fine too. I prefer this one. This is what we use in physics. And how do we measure frequency? Do we use units of length for frequency? I don't want the formula. We're going to talk about that in a second. Almost. Second is how we measure period. And you had talked about period before. Frequency is almost like the reciprocal of period. In fact, it is the reciprocal of period. Frequency is how many waves pass in a given amount of time, whereas period is how much time it takes for one wave to pass. So period we would measure in time. Frequency we measure in inverse time units. For instance, like 1 over seconds. That's the usual one, and that equals the unit hertz. So Hz, capital H, lowercase z, named after a man called Hertz. Probably first name Heinrich, I would guess. I don't actually know. But 1 over second, so an inverse seconds. A lot of times in upper level literature, you'll see it indicated as seconds to the negative first power, which, as you know, being astute learners of mathematics, this is 1 over seconds. In the same way that 2 to the negative first power is 1 over 2, right? So hertz is what we use to measure frequency. What do we use to measure wavelength? Units of length. Usually what in the SI? No, usually just, no, what did you say? Meters, just meters usually. Meters. Usually what we do for this is we measure the wavelength in something like, we could say for instance like the wavelength of light, I think, or of red light in the visible light spectrum is 400, or maybe we could say 4.0 times 10 to the negative 9th meters. And this tells us everything we need to know. Like this way we don't have to use little prefixes, although we could also call it, I think this is about 400 nanometers. We could use nano. I think what I indicate here actually has to be 0. But anyway, this is usually more convenient. We usually just measure the wavelength in meters and then forget about the little prefixes, although you'll see it both ways. I think on your test you'll only see it this way though. So now the math. Let me make sure that there's nothing else conceptually I want to cover before we talk about that. The last lesson here in your book talks about the different ways that waves interact. Things like reflection, refraction, diffraction, interference. Have you read that? If you can define each of those things and give an example, why don't you write this down somewhere? If you want to write something down, you usually like pick up your pencil like this, and then you can be prepared to start writing. And we'll do some of these in the lab, and we'll talk about them on your chapter review, but I just want to make sure that I want to have it on video that you know that you're supposed to know this. Reflection, refraction, diffraction, and interference. Where did I get those from? Yeah, you can tell because you could hear the pages move as I was doing it. If you can define those, you might write this down too. If you can define those and give an example, that will be sufficient for your test. They're in your book. They're the blue headings in lesson 3. Reflection, refraction, diffraction, and interference. It also has standing waves and resonance. We already talked about resonance in the laboratory, and we'll do standing waves as part of our demonstration. So you'll have some familiarity with these. But those are the ones you need to know. And you already know what reflection is, and probably you know what refraction is. And if you read your book at all, you should know what diffraction is too. But I do want to talk about the math. That's the main thing that I want to have on video so you have record of this. The primary piece of mathematics we're going to do in this chapter is this formula V equals lambda, and I'm going to use, I decided just now because your book does, and because it makes it easier, V equals lambda F, where V, we should have a little arrow over it, is what? Probably. You remember from, September, yeah. Say it again. No, you said the wrong one. Velocity. Velocity. Lambda, we just said, is and the curly Latin F is, can you just make a wild guess, Peyton Moreva, why I wanted to use the Latin letter F after all instead of nu? Yeah, so I don't mix it up with what? Well, look, I have V here, and you remember my saying that the nu, the way I tell that apart is I put a little line on the end of it. So it'd just be easier if you use the F, probably. So velocity, let's look at these actually first. How did I say we measure frequency? What unit do we use to measure frequency? Let's all think about it before we just answer. Hertz. And what is a hertz equal to in the SI? 1 over seconds. Okay, what do we usually measure wavelength in? Meters. And what mathematical operation am I doing between the wavelength and the frequency? I'm multiplying. So if I multiply meters times, remember, 1 over second, what am I going to end up with for my velocity? Meters times 1 over seconds. No? Oof, haven't you guys taken algebra? What's this? You've seen algebra before, right? What's the answer to this? Okay, so let's try again now with just some very much less complicated letters. Meters over seconds. What do we call that in science? Meters over seconds. What do we say that as in science? But how do we pronounce this? Meters per second. Is that a valid unit of velocity? Yes, that should ring a bell. Does it make sense then for velocity to be measured in meters per second if wavelength is measured in meters and frequency is measured in hertz? Yeah, it has to. This is why units are important, is because this, well, to people who know algebra, this makes a lot of sense. I guess maybe that does or does not include some of you. But velocity, we measure in meters per second. Can we manipulate this equation so that we can find anything? For instance, what I mean by that is if instead of given a wavelength and a frequency, if they tell me the wave speed, or I said wave speed, wave velocity, doesn't really matter. They will use those interchangeably. But if they give me the wave speed and the wavelength, could I find the frequency? Yeah. What am I going to need to do first every single time? Let's review this from actually, we haven't done this kind of math for quite many months, so let's review this. What should I always do every time first when we do? Write the raw equation. Thank you, Sire. So anytime, actually, let's look together at page 299. So if everyone could put their page to 299, put their page, stupid. If they could turn their book to the page 299. A wave. Number 1 on the bottom in the practice problems where I am, and we're all going to look at it. It's in the blue shaded box. A wave traveling in water has a frequency of 500.0 hertz and a wavelength of 3.00 meters. What is the speed of the wave? Well, no. You don't just do anything. First, you have to do what? There are steps. Raw equation. First I V equals lambda F. This is a waste of my time. I shouldn't have to write this stupid equation every single time. It kills me to do this. Why though? Explain to me. Why is the mean jerk making you write this every single time? There are 2 reasons. Okay, yeah, so that you remember to do it, and you probably memorize the equation. So you remember is what Justin says. What's the other reason? How liable are you to mess this up? Even if, just as Tatum says, even if you just multiply these together, how liable are you to mess this up? No, not easy at all, I would say. You're just going to multiply 2 things together from your book. How easy is that to mess up? No, not very easy. But, and that's in this case, but what if you have to start manipulating them? Well, a little bit harder. Or what if you start having an equation like the drag coefficient equation, where it's got 4 different variables and 3 different coefficients in it? Well, that is pretty easy to mess up. So the point is, and this is the whole reason when young people, or even freshmen, not all of them are people, but when individuals ask me, why do we need to know this? It has nothing to do with, you might never see wave speed again in your life. You might, but you might never. The point is, if you can do this process, and you can do it right every single time, whether it's easy or difficult, you can do other processes in your life, like filling out your trucker log, or filling out your hours from Arby's, or whatever you're going to do in your life. If you can't do this, no, listen, you think, well, I'm never going to be too stupid to fill out a trucker log. If you can't do this, and you can't follow the rules, you're going to get fired. Great fire. And I'm not going to feel bad for you because you never learned how to do things the right way. Here's the right way. V equals lambda F. We write that every single time. Next, we do what? What's the next step? 2. Let's use the other word. Yeah, substitute. So V equals now. What was lambda from the equation or from the book? No. Yeah, it is wavelength, but what is the value? 3.00 meter. We should include our unit because that's who it is. The unit is the noun of this little phrase here. 3 means nothing. 3 meters means a lot. Okay? What is the frequency? 500.0 hertz. The reason these points are important is because they tell us the precision of this. If it just says 3, it may have been rounded. It could be anywhere from 2.449, it could be something lower than that even, to 3.444. I don't know. I mean, this means, if it just says 3, it means nothing. This tells us that it was measured to the hundredths place and found to be exactly 0, which that's a valuable thing to say. So 3.00 times 500.0 equals what? 1,500. We have what are called 3 significant figures, so we need to have a line over our 0. We'll talk about that more when you're in chemistry. Meters per second is the correct unit. 1,500 meters per second. Then you ask yourself, is this a valid unit for velocity? I hope you find that it is. Yeah, it is a valid unit for velocity. Does it make sense for a wave to have a velocity of 1,500 meters per second? That you don't really know yet. That is a reasonable velocity for a wave, but you don't really know yet. Okay, next one. The lowest pitch sounds. The lowest pitch The lowest pitched sounds humans can hear have a frequency of 20.0 hertz. What is the wavelength of these sound waves if their speed is 340.0 meters per second? What should I do first? Right, the raw equation. V equals lambda. Uh-oh. What's the uh-oh here, young people? Yeah, we already have the velocity, so this equation is bad. And, okay, and now here I'm going to ask you the next question, Colton. This is just for Colton, so everyone else pipe down. Should I, Colton, there are two choices here. Should I manipulate this equation, or should I substitute and then manipulate? Let me ask one other person. Justice, should I manipulate this equation, or should I substitute and then manipulate? I should manipulate first. Remember, step 1 is write the raw equation, and step 1.5 that we don't always need is to manipulate. How should I manipulate this so that I'm finding, what am I trying to find here? Well, let's read the equation again, or the question again. It says, what is the wavelength? So what should I solve for here? Yeah, lambda. So I need to get lambda by itself. So how can I manipulate this so that lambda is by itself? Justice? Divide both sides by frequency. V over F equals lambda. Now then I do what? Now I substitute. What's the velocity in this case? 340.0 meters per second. What's the frequency in this case, Rhett? It is not. It's 20.0 hertz. Okay, what then will be the wavelength? Well, 340 divided by 20 is the same as 34 divided by 2, which is 17. In this case, 0.0. What's my unit going to be? Would it make sense for the wavelength to be measured in meters? Yep, wavelength must be in length units. Now, let me show you a little bit more specifically how did this units cancel out. So we had if we forget about the numbers, which remember the numbers are not very important, if we have meters over seconds over hertz, right? You see how this came from that? Yeah? If I have hertz, remind me, what's hertz the same as? 1 over seconds. And remember that dividing two fractions looks like this. So I have now meters over seconds times seconds over 1. Because remember, it was 1 over seconds, but I divided it, so I flip it. Remember dividing fractions. What happens to my seconds? You don't say cancel. Mr. Stintley will come in here and he'll start you on fire. Seconds do what? What Mr. Stintley wants you to say, and what I want you to say is they reduce to 1. So these reduce to 1, and we're left with 1 for that. Meters times 1 is meters. Divided by 1 is meters. Wow. Do you have questions about the math? That's the main thing I want you to understand. Colton. Shh. Yeah, okay, you could say it's for the sake of your sanity. It helps you with this one. It's not like you wouldn't be unable if you substitute first to manipulate it. It'd be more difficult because instead of rearranging 3 letters, one of them is Greek, you'd be rearranging all these numerals, which you might get confused, but you're not that stupid. You probably wouldn't get that confused. But when it becomes more complicated and you have more than what's called a one-step manipulation, it really is, it scales exponentially intelligence. So even if you're an extremely smart person, if you have like 5 variables and one of them is raised to a certain power and you have also 2 coefficients in there, it will throw you off, even if you are the best mathematical. Bye.